In the summer of 2020, a satellite drifting over the Siberian Arctic recorded something that stopped a team of climate researchers mid-sentence. The permafrost, the frozen ground that covers nearly a quarter of the northern hemisphere's land surface, was releasing methane in a pattern the instruments had never detected before. Not a trickle, not a gradual seep, a pulse, like something breathing. The numbers were wrong. Not wrong in the sense that the equipment had failed. Wrong in the sense that the readings shouldn't have been possible yet. According to the models, this level of methane release wasn't supposed to happen for another 30 years. It was 2020. The scientists looked at each other. Then they looked at the data again. It was still wrong, still impossible, still real. Somewhere above the Arctic Circle, a crack roughly 300 kilometers long is widening. It has no name most people would recognize. It doesn't trend on social media. It doesn't appear on the evening news between the weather and the sports scores. But it exists, measurable, growing, documented by satellite imagery that is updated every 48 hours. The crack is part of a larger system of fractures, forming across what scientists call the Arctic Permafrost Zone, a band of permanently frozen ground that stretches across Alaska, Canada, Russia, and Scandinavia. For the last 10,000 years, this ground has been frozen solid. Not ice on the surface, ice inside the Earth, frozen soil, frozen carbon, frozen methane, locked in geological cold storage since before the first human civilization built its first wall. That cold storage is failing, and the speed at which it's failing has, in the last 5 years, begun to alarm even the researchers who study it for a living. To understand what is happening in the Arctic right now, you have to understand something most people have never thought about. The ground beneath the tundra is not empty. The Arctic permafrost zone covers approximately 23 million square kilometers. To put that in perspective, that is more than twice the size of the continental United States. Beneath the surface of this vast, largely treeless landscape, the frozen ground extends downward, in some places 100 meters, in others more than 1,500 meters deep. Solid, cold, stable, or it was. Permafrost contains something that makes it uniquely dangerous as the climate warms: carbon. An estimated 1.5 trillion metric tons of organic carbon is locked in the frozen soil, the accumulated remains of plants, animals, and microorganisms that have been dying and freezing for millennia. This carbon was never fully decomposed. It was simply frozen before that process could complete. Frozen carbon is inert. Thawed carbon is not. When permafrost melts, microorganisms that have been dormant for thousands of years begin to wake up. They go to work on that ancient organic material. And as they do, they release two things: carbon dioxide and methane. CO2, the more familiar greenhouse gas, is dangerous enough. But methane is roughly 80 times more potent as a warming agent over a 20-year period. The Arctic is not just melting, it is beginning to exhale. There is a phrase climate scientists use that tends to get lost in the noise of the broader climate conversation. It is 2 words, and it describes the thing that keeps some researchers awake at night more than almost anything else: feedback loop. Here is what it means in the context of the Arctic. Warmer air melts the permafrost. Melting permafrost releases methane and CO2. Methane and CO2 warm the atmosphere further. A warmer atmosphere melts more permafrost. More permafrost releases more methane. The atmosphere warms more. Each step triggers the next. The cycle has no natural break. This is not a linear process, where X degrees of warming causes X amount of permafrost loss. It is a compounding process, where each degree of warming accelerates the next one. Scientists call this a positive feedback loop, which is perhaps the most misleading name in all of science. There is nothing positive about it. It means the system amplifies itself. For decades, climate models treated permafrost carbon as a slow variable, something that would seep out gradually over centuries, contributing modestly to warming projections. Those models are being revised. The revision is not in a favorable direction. Recent data from the Siberian Arctic has introduced a phenomenon that most people outside the scientific community have never heard of: abrupt thaw. Unlike gradual permafrost thaw, which happens evenly over large areas over long periods, abrupt thaw is sudden, localized, and dramatic. It occurs when a section of frozen ground collapses inward, creating what geologists call a thermokarst, a landscape that looks like the surface of the Earth was punched from below. Lakes form overnight where there was dry tundra the day before. Hillsides that were stable for centuries slide into newly formed craters. Coastlines collapse into the sea at rates of several meters per year. In some areas of Siberia and Alaska, the ground is literally swallowing itself. The technical term for this process makes it sound almost mundane, retrogressive thaw slumping, but the scale of it is anything but. In 2019, a research team surveying permafrost degradation in the Canadian Arctic noted that landscape features they expected to see developing over 15 to 20 years had appeared in less than a single summer. Not slowly, not gradually, overnight. One researcher described it as watching decades happen in weeks. The satellite data covering the Arctic permafrost zone has, over the last decade, revealed something that is difficult to process even when you understand what you're looking at. The landscape is fracturing. Not metaphorically, literally. Ground that was frozen and stable is cracking open in patterns that satellite imagery records as dark lines spreading across the white and brown of the tundra. A network of fissures growing each year like cracks in old plaster. Except the plaster is the foundation of one of the most important climate systems on Earth. These cracks, called thermokarst troughs, thermal erosion gullies, and retrogressive slumps, depending on their specific form, are increasing in number and expanding in size at a rate that has accelerated noticeably since approximately 2018. A 2021 study, published in Nature Climate Change, found that the area of abrupt thaw features in the Arctic had increased by an estimated 60% over the previous 2 decades. The rate of increase in the final 5 years of that period was roughly double the rate of the first 15. In parts of Siberia, permafrost that was frozen solid 30 years ago has now thawed to a depth of several meters, exposing sediments that, in some areas, have been frozen since the Pleistocene, since before modern humans existed. The carbon locked in those sediments has been waiting for 30,000 years. It is no longer waiting. But there is something else in the satellite data that does not receive as much attention as the permafrost cracks, something that took researchers longer to piece together, because the scale of it made it initially difficult to recognize. The Arctic Ocean itself is changing. The East Siberian Arctic Shelf, the vast, shallow seafloor that stretches across much of the Russian Arctic coast, is one of the most methane-saturated environments on Earth. Beneath it, frozen in what are called submarine permafrost deposits, lie reserves of methane that dwarf the carbon stored in the terrestrial permafrost above. The seafloor permafrost of the East Siberian Arctic Shelf is estimated to contain between 500 and 5,000 gigatons of methane, compared to the roughly 1.5 trillion tons of carbon in terrestrial permafrost. The range of that estimate is large because the measurements are difficult, the data is incomplete, and the implications of getting it wrong are severe enough that scientists tend toward caution in how they characterize it. What is not in dispute is that the seafloor permafrost is warming. Since the early 2000s, water temperatures on the East Siberian Arctic Shelf have increased. Sea ice, which historically acted as an insulating layer between cold Arctic air and the ocean, has retreated dramatically. Without that insulation, the ocean absorbs more heat in summer. That heat, transferred to the seafloor, is working on permafrost that in some areas is only a few meters thick. In 2020, a Russian-American research team reported detecting methane plumes rising from the seafloor of the East Siberian Arctic Shelf at concentrations significantly higher than background levels. They described some of the plumes as ebullition, bubbling, which indicates not a slow seep, but an active release driven by pressure from below. The seafloor is exhaling too. Here is the uncomfortable truth about what is happening in the Arctic right now. It has happened before. Not recently. Not in any time frame that a human mind intuitively grasps, but it has happened. And the record of what it looked like, written in ice cores, ocean sediments, and rock formations, is one of the reasons climate scientists use words like tipping point and irreversible when they talk about the permafrost system. Approximately 55 million years ago, during a period geologists call the Paleocene-Eocene thermal maximum, the Earth's climate underwent a rapid warming event. Over a period of roughly 20,000 years, rapid by geological standards, global average temperatures rose by somewhere between 5 and 8 degrees Celsius. The leading hypothesis for what triggered this event: a massive, relatively rapid release of carbon from frozen reservoirs, possibly methane hydrates on the seafloor, possibly permafrost carbon on land, possibly both. The feedback was real. The warming was real. The consequences lasted millions of years. But that was 55 million years ago. Surely the modern situation is different. There is a closer example. During the last deglaciation, approximately 14,000 years ago, as Earth emerged from the last major ice age, rapid melting of Arctic ice triggered significant methane release from thawing permafrost. Ice core records show a dramatic spike in atmospheric methane concentrations over a period of just a few hundred years. This event, sometimes called the Bowling-Alerod transition, corresponds to one of the fastest warming periods in the recent geological record. The Arctic has a memory, and its memory suggests that, once the thaw begins to accelerate, it does not slow down easily. Let's talk about specific data, because the data is where the real story lives. The Arctic is warming at a rate approximately 4 times faster than the global average. This is not a forecast. It is a measured fact, documented in temperature records going back to the mid-20th century, and confirmed by multiple independent research institutions, including NASA, NOAA, and the European Space Agency. In 2023, average annual temperatures in parts of Siberia and the Canadian Arctic reached levels that exceeded historical averages by more than 3 degrees Celsius. Individual summer months in some Arctic regions registered anomalies of 5 to 6 degrees above the long-term mean. Permafrost temperature, measured by instruments installed in boreholes drilled into the frozen ground, has increased by an average of 0.3 degrees Celsius per decade since the 1990s in Alaska. In some parts of Siberia, the rate is nearly double that. At first glance, 0.3 degrees per decade sounds trivial. It is not. Permafrost thaws at a threshold. Once the temperature of frozen ground crosses 0 degrees Celsius, the physical state of the soil changes irreversibly. It is not like a human body cooling down and warming up. When permafrost thaws, the carbon is released. The structure changes. The ground sinks. It does not refreeze simply because winter comes. The area of Arctic permafrost showing signs of active degradation has increased by an estimated 25% since the 1970s. That number will be larger by the time you finish reading this. The methane numbers are particularly striking. Atmospheric methane concentrations globally reached approximately 1,923 parts per billion in 2023, more than 2.5 times higher than pre-industrial levels. The rate of increase in atmospheric methane has accelerated since 2007, with the steepest rises recorded in the most recent years of available data. Identifying the precise sources of this methane increase is technically difficult, and scientists are careful about attributing all of the rise to Arctic permafrost. Other sources, agriculture, fossil fuel extraction, tropical wetlands, also contribute. But the signature of the methane, its isotopic composition, the atmospheric patterns in which it appears, points clearly to a growing Arctic component. In a paper published in Science in 2021, a team of researchers modeled the potential contribution of permafrost methane to future warming. Their projections suggested that, under current warming trajectories, permafrost thaw could add the equivalent of an additional 0.3 degrees Celsius of global warming by 2100, on top of all other warming. And that estimate assumed a relatively moderate rate of abrupt thaw. We are not saying collapse is inevitable, one of the lead authors noted in a follow-up interview. We are saying we don't know at what temperature it becomes inevitable, and we don't know how close we already are to that temperature. Let's be specific about the physical evidence that is visible right now, today, to anyone with access to satellite imagery. The Batagaika crater in Siberia, Russia, is perhaps the most dramatic single example of what permafrost collapse looks like at scale. It is sometimes called a megaslump, a depression formed by the collapse of a hillside as the permafrost within it thaws, and the ice that gave the hill its structure melts away. Batagaika is roughly 1 kilometer wide and 100 meters deep. From above, it looks like a wound cut into the tundra, a dark, curved gash in the otherwise flat landscape. Local Yakut people have a name for it, the gateway to the Underworld. It did not look like that in 1991. In 1991, the The Batagaika crater was a small erosion scar, something a researcher might note in a field survey, and probably did. By the time it was formally documented in scientific literature in 2017, it had become one of the largest thermokarst features ever recorded. It is still growing. By some estimates, it grows by 10 to 30 meters per year. And Batagaika is not unique. It is not even the largest. In the last decade, satellite surveys of the Siberian Arctic have identified dozens of similar structures, and hundreds of smaller ones, forming or expanding across the permafrost landscape. In northern Alaska, USGS researchers documented a stretch of coastline on the Beaufort Sea that is eroding at more than 17 meters per year in some sections. The ground is not wearing away slowly. It is collapsing into the ocean in large chunks as the permafrost beneath the coastal bluffs thaws and loses structural integrity. Villages that have existed for generations are falling into the sea. This is not a forecast. It is happening now. Here is where the story stops being only about science. Approximately 4 million people live above or near the Arctic permafrost zone. Most of them live in Russia, in cities and towns built on the assumption that the ground beneath them would remain permanently frozen. That assumption is now being tested by physics. The Russian city of Yakutsk, home to approximately 280,000 people, is built almost entirely on permafrost. The infrastructure of the city, including its buildings, roads, pipelines, and utility systems, was engineered for frozen ground. When that ground thaws, even partially, the consequences are immediate and structural. Since the 1990s, the number of buildings in Yakutsk showing significant structural damage related to permafrost degradation has increased substantially. Walls crack, foundations tilt. Some buildings have become uninhabitable. The cost of maintaining infrastructure in permafrost zones across Russia is projected to reach hundreds of billions of dollars in the coming decades. But Yakutsk is just one city. The permafrost zone extends across roughly 65% of Russia's land area. Much of Russia's energy infrastructure, pipelines, well pads, processing facilities, was built on permafrost. The Trans-Siberian Railroad crosses permafrost for thousands of kilometers. Airports, military installations, and communications infrastructure across the Russian Arctic rely on frozen ground for their structural integrity. The International Permafrost Association has estimated that by 2050, the permafrost degradation already underway could put infrastructure worth an estimated $35 trillion at risk globally. In Alaska, the story is similar. The village of Yakutsk, once home to about 375 Yupik people, has been in the process of relocating for more than 15 years because the permafrost beneath it has thawed to the point where the ground is no longer stable enough to support the community. The school was sinking, the runway was deteriorating, the bank of the Ninglik River, no longer reinforced by frozen ground, was collapsing at a rate of 3 to 4 meters per year. Yakutsk has moved. Other Alaskan villages are in the process of moving. Others are waiting for funding to begin. The question of how many communities ultimately become uninhabitable because of permafrost degradation, in Alaska, in Canada, in Russia, in Scandinavia, is one that nobody has a comfortable answer to. The consequences of Arctic permafrost collapse are not confined to the people who live there. They extend, through a chain of systems, to the rest of the world. Consider this: the Arctic contains the largest remaining undeveloped oil and gas reserves on Earth. Extraction of those reserves, already underway and under expansion in Russia, Alaska, and Canada, depends almost entirely on frozen ground. Roads to drilling sites are built on permafrost. Pipelines are suspended on pilings designed for permafrost. Well pads require frozen ground to maintain their structural integrity during operations. As permafrost degrades, the cost and difficulty of Arctic resource extraction increases dramatically. More importantly, some of the largest existing extraction infrastructure is already beginning to show signs of instability. Portions of the Trans-Alaska Pipeline System, one of the most critical pieces of energy infrastructure in North America, transporting approximately 500,000 barrels of crude oil per day, cross permafrost zones that are actively degrading. The pipeline was originally engineered with permafrost thaw in mind. Special thermal devices were installed to keep the ground frozen around certain supports. But the rate of warming in Alaska now exceeds what those designs anticipated. The pipeline is monitored continuously. So far, its structural integrity has been maintained. But engineers are already designing modifications for a warmer future, modifications that will cost tens of millions of dollars, and may not be sufficient if warming continues at its current pace. Then there is the carbon accounting problem that the world has not fully confronted. Current international climate agreements, including the Paris Agreement, set emission reduction targets based on models that did not fully account for Arctic permafrost emissions. The carbon released by thawing permafrost is not counted in any nation's emissions inventory. No country owns it. No treaty governs it. It is a massive, growing carbon source that exists entirely outside the architecture of global climate policy. The emissions that humans produce and that governments track and attempt to reduce, those represent roughly 40 billion tons of CO2 equivalent per year. The estimated carbon pool in Arctic permafrost is 1.5 trillion tons. Even releasing a fraction of that would significantly alter the trajectory of global warming, and the release is already underway. Science is at its most important, and its most uncomfortable, when it knows enough to be alarmed, but not enough to be certain. That is precisely where permafrost science stands today. Here is what is known with high confidence. Arctic temperatures are rising at approximately 4 times the global average rate, and this trend has been consistent and accelerating for decades. Permafrost temperatures are increasing across the Arctic. The area of actively degrading permafrost is growing. Methane and carbon dioxide emissions from permafrost are measurable and increasing. The physical landscape of the Arctic tundra is changing in ways that are visible from space and unprecedented in the historical record. These are not projections, they are measurements. Here is what is significantly less certain. At what temperature does the permafrost system cross from gradual degradation into abrupt, self-sustaining collapse? Is there a tipping point? A specific threshold of warming beyond which the feedback loop becomes impossible to interrupt? If so, how close is the current Arctic temperature to that threshold? And when, not if, but when, that threshold is crossed, how fast does the cascade unfold? The uncertainty is real. The uncertainty is also not reassuring. The honest answer from the research community is that the models consistently underestimate the rate of permafrost degradation when compared to observations. Real-world thaw is happening faster than the models projected, consistently, which means that if the models are wrong about the rate, they may also be wrong about the threshold. A 2023 literature review examining 100-plus permafrost studies found that actual permafrost degradation was outpacing model predictions in roughly 70% of cases reviewed. The gap between prediction and observation has widened as warming has accelerated. One researcher, working in the Yukon-Kuskokwim Delta in Alaska, described the experience this way. We have graphs that show where we expected the degradation line to be in 2040. We are already past that line, and it is 2024. There is a phrase that circulates in climate journalism and social media, and it is one that many permafrost scientists find deeply frustrating: methane bomb. The frustration is professional. The image of a bomb implies a sudden, catastrophic detonation, a single event, a precise moment. Permafrost thaw does not work that way. It is a process, not an explosion. It happens over years, decades, possibly centuries. The scientists who study it most closely resist the bomb metaphor because it implies inevitability and suddenness that the current data does not fully support. And yet, the instinct behind the metaphor is not entirely wrong. The energy stored in Arctic permafrost carbon is real. The potential for that carbon, once released, to trigger additional warming, which triggers additional release, is real. The models that attempt to quantify the upper bound of what permafrost thaw could contribute to global warming produce numbers that, in their worst-case scenarios, are genuinely alarming. In 2022, a team of researchers at the University of Leeds published a study modeling what they called permafrost tipping cascades, scenarios in which permafrost thaw in one region triggers warming that destabilizes permafrost in adjacent regions, which triggers further warming in an escalating sequence. Their conclusion: such cascades are possible, though not certain, under warming trajectories that current global emissions are consistent with. Possible, but not certain. That phrase appears with uncomfortable frequency in the permafrost literature. The scientists are not saying disaster is inevitable. They are saying they cannot rule it out. And they are saying that the longer current warming trends continue, the smaller the window becomes to determine whether a tipping cascade is actually in progress before it becomes irreversible. There is another dimension to the Arctic story that is rarely discussed in the context of permafrost science, but is inseparable from it: geopolitics. As sea ice retreats, new shipping routes open. The Northern Sea Route, which runs along Russia's Arctic coast, has become commercially viable for a significantly longer portion of the year than it was in the 1990s. Transit times between Europe and Asia via the Northern Sea Route are substantially shorter than via the Suez Canal. Russian state shipping company Sovcomflot, along with Chinese maritime interests, has invested heavily in Northern Sea Route infrastructure. The retreat of sea ice also makes previously inaccessible Arctic seafloor resources available for potential extraction. Russia, Canada, Denmark, through Greenland, Norway, and the United States have overlapping claims to the Arctic continental shelf, claims that include potentially vast reserves of oil, natural gas, and mineral deposits. The paradox is brutal. The warming that is destabilizing the permafrost and accelerating methane release is also making it easier and more economically attractive to extract and burn the fossil fuels that drive further warming. Russia has been explicit about this calculation. Russian state policy treats Arctic warming not primarily as a catastrophe to be mitigated, but as an economic opportunity to be managed. New Arctic infrastructure is being built. New extraction projects are being approved. The fact that the ground beneath those projects is thawing, literally destabilizing the infrastructure as it is being constructed, is treated as an engineering problem, not a strategic one. Meanwhile, indigenous communities across the Arctic, Yupik, Inupiat, Athabaskan, Nenets, Yakut, Inuit, who have lived in relationship with this landscape for thousands of years, are watching the world they know dissolve. Ice roads that once connected remote communities are failing earlier each year, cutting off supply chains and access to medical care. Hunting grounds are moving or disappearing. Coastal villages are being consumed. Their testimony is not peer-reviewed. It does not appear in the pages of Nature or Science. But it has been consistent, specific, and, as the scientific data increasingly confirms, accurate. Given everything that is at stake, the question of how closely the Arctic permafrost system is being monitored deserves attention. The answer is imperfectly, and with significant gaps. The Global Terrestrial Network for Permafrost maintains a network of approximately 1,000 boreholes across the Arctic, measuring permafrost temperatures at depth. This sounds substantial until you consider that the network covers 23 million square kilometers, roughly one monitoring site per 23,000 square kilometers of frozen ground. Satellite systems, ESA's Sentinel series, NASA's NISAR mission, various commercial Earth observation platforms, provide surface coverage with increasing resolution and frequency. They can detect ground deformation, track the growth of thermokarst features, and measure methane concentrations in the atmosphere above the permafrost zone. What they cannot do, with current technology, is measure carbon flux from the ground at the precision required to accurately quantify total permafrost emissions. The International Space Station carries instruments capable of detecting methane from orbit. Aircraft equipped with gas analyzers conduct sampling flights over key Arctic regions. Research stations in Alaska, Canada, Russia, and Scandinavia operate continuous monitoring equipment. But the permafrost zone is vast, mostly uninhabited, and insignificant politically complicated to access. The data coverage is improving, but it remains incomplete. The result is that major events, large-scale abrupt thaw, significant new methane sources, may go undetected or be identified only after the fact, when satellite imagery is reviewed weeks or months after the event occurred. The thing about feedback loops is that they are easiest to interrupt early. The later they are identified, the harder they are to influence. In the scientific literature, researchers are careful. They qualify. They note confidence intervals and acknowledge uncertainty. They write things like, under high warming scenarios, and if current trends continue. But in the background of careful scientific language, there is a scenario that the models produce and that nobody in climate policy is quite willing to speak about plainly. It goes like this. Global temperatures continue to rise at or above current trajectory, roughly 2.5 to 3 degrees Celsius of warming by 2100. As Arctic temperatures cross 4 to 5 degrees above pre-industrial levels, abrupt thaw of submarine permafrost on the East Siberian Arctic Shelf accelerates. Methane release increases significantly. The additional methane warming triggers accelerated terrestrial permafrost degradation across Siberia, Alaska, and Canada. More carbon dioxide and methane enter the atmosphere. Warming accelerates further. The permafrost tipping cascade becomes self-sustaining. Under this scenario, the contribution of permafrost carbon to global warming would be large enough to push actual 21st century warming substantially beyond the projections that current climate models produce. Projections that are themselves severe enough that the global community has spent 30 years attempting, with limited success, to prevent. This scenario is not considered likely. But it is also not considered impossible, and here is what makes it uniquely alarming. Under current global policy frameworks, there is no mechanism designed to address it. The permafrost system is not in any climate treaty. It cannot be regulated. Its emissions cannot be taxed or capped. It is an autonomous Earth system, responding to temperature, independent of human decision-making. Once it crosses a certain threshold, human choices become largely irrelevant to its trajectory. The question of whether that threshold has already been crossed, or how close to it we currently stand, is one that the best-equipped researchers in the world cannot definitively answer. There is an image that stays with you once you've spent time inside this data. It is not a dramatic image. It is subtle, understated in the way that the most genuinely alarming things often are. It is a graph of permafrost temperature from a borehole in the Russian Arctic, measured every 6 months for 30 years. On the left side of the graph, the line is relatively flat, fluctuating slightly with seasons and climate variability, but holding roughly stable. In the middle, the line begins a slow, almost imperceptible rise. On the right side, the line curves, not sharply, not dramatically, but consistently. Every data point for the last 12 years is higher than the corresponding point from 20 years before. No year reversed the trend. No winter cold enough to arrest it. The line continues upward, toward the right edge of the graph, which represents the present. And then it stops, because the data stops there. We do not know where it goes after the right edge of the graph. We do not know whether the curve continues to rise gradually, or whether somewhere just beyond what we can currently see, it begins to steepen. That is the honest state of knowledge about the Arctic today. The crack is still widening. The methane is still rising. The permafrost temperature is still climbing. The satellite instruments are still running their automated sweeps, recording ground deformation in millimeter increments, flagging anomalies, uploading data to servers in Fairbanks and Potsdam and Moscow. None of those instruments has signaled that the system has stabilized. Not one of them has shown a year where the trend reversed. The Arctic is cracking open faster than scientists expected. And the most important data point, the one that tells us whether the fracture can still be stopped, has not yet been recorded.